cheese sandwich.
Can we make it ham this time?
Yeah, I agree.
Cheese sandwiches are boring. That's a grilled
I think we should
cheese.
stick with cheese. Make sure we don't get confused.
You like grilled cheese?
That's thermodynamics.
What?
That's thermodynamics if you grilled cheese. 'Cause you've got to. Okay, we're going?
Yeah.
Okay. All right, so since you all didn't like the cheese sandwiches, I'm going to make ham sandwiches. Okay? I can multitask. So here's the story. So the ham sandwich, boring as this is, but I need different numbers. So that's going to consist of 2 slices of bread, 1 slice of ham, and this is going to be a synthesis reaction where I'm going to produce ham sandwiches. Okay? Now, you need to have this visual. So we're going to have visualize like a wall inside the kitchen. Okay? And so on this side of the table, or this side of the wall, there's going to be a table. And Isaac is going to have all of these slices, this big stack of ham, and this big slice of bread. So he's got lots of ham, lots of bread. Okay? And I'm over here with nothing. Okay? I got nothing to start with. All right? I have no sandwiches. But here's going to be how this game is going to play. So Isaac is going to make a sandwich, and then he's going to throw it over the wall. Okay, so he's going to throw over the wall a completed ham sandwich. Okay? Now, I'm going to be a jerk. I'm going to go, hey, whatever. So I'm going to take the sandwich, and I'm going to decompose it back into the 2 slices of bread and 1 slice of ham. And then I'm going to throw those back across. Okay? So he's going to throw me sandwiches, completed sandwiches. I'm going to throw back to him 2 slices of bread, 1 slice of ham. Okay? But then he's going to take that and he's going to make a sandwich and throw it back over to my side. Okay? So if you look at this in terms of changes in concentration, right? So let's just look at this. Just look in terms of like stoichiometry. So let's say that Isaac is going to throw 5 sandwiches over to me, right? Okay. So if he's going to throw 5 sandwiches over to me, how many slices of ham is he going to go through?
5.
5 what?
Because there's 1 ham per sandwich.
Yeah. So if you do the stoic, right? So if he makes 5 sandwiches, if you look at the sandwich, down here you go, okay, right? For every 1 sandwich, if you go up there to the stoic, oh, that's 1 slice of ham. Okay? So if he makes 5 sandwiches, he went through 5 slices of ham. Okay? Basic idea, right?
Let's say bin on the bottom.
Huh?
It's sandwiches.
B28.
Yeah.
Does that say Ben on the
I thought it sounded bad.
It's a freaking maturity thing.
Alright,
Okay.
B28. So
Now, how many slices of bread would he go through?
10.
double it.
What?
Because it's B2H.
So, in terms of bread, it's 5 B2H, right? And then for every 1 sandwich, that requires 2 slices of bread, right? Okay, cool. He's going to go through 10 slices of bread. Nice. Now, we can look at this in terms of a rate function, okay? So in terms of a rate function, if he's going to make these sandwiches over here, what's going to happen? Let's just focus on what Isaac is doing. As he makes sandwiches, what happens to the concentration of the slices of bread and the slices of ham?
Down.
It's going to go down. And the concentration of the sandwiches is going to go up. Okay? So as one goes down, the other one goes up. Now, if you look on that sheet of lecture notes that I gave you, okay? So if you, and I've given you this kind of generic of idea of A, B, B, C, D, D. So there's some, I'll show you two different ways that you can think of this theory. Some people would like just a pure kind of a formulary way approach to it. Some people like a stoichiometry approach to it. So here's the story. So if you look at this in terms of if you wanted to go with this generic thing. First off, notice there's an equality sign in there. So you have the inverse, this -1 of the reactant. So let me explain what the -1 in terms of like if you were to go with this general formulary thing. So the negative on the reactants is just indicating that those concentrations are going to be decreasing. The positive products, those are positive numbers because those concentrations are going to go up. Okay, so that's why, that's what the negative signs are doing, because those concentrations are going to go down as the reaction takes place. So if you were to look at this in terms of this analogy with a ham sandwich, so what this is giving you is a way to express what this is in terms of function. So you've got all of these have -1 or +1 over whatever the coefficient is. So if you were to look at this in terms of what we just did, so with the bread, you would have -1 over 2, because there's a coefficient of 2 in front of the bread. And then it's always the delta change, okay? So this would be like the change in bread per unit of time, okay? Now, there's another equal sign that says, oh, okay, right. So that's going to equal, I should have written this all out, but just imagine this is all one big line. So then for the ham, that would just be -1, change in the concentration of ham over a unit of time. And then with the sandwiches, that would just be the change in the concentration of bread or the sandwiches per unit of time. So this is how this works. So let's say that we measure the formation of sandwiches. And we keep track of, hey, Isaac is really good at making sandwiches. All right. So Isaac can make 20 sandwiches per minute. Okay. He's really good at making, of course, it's only 2 slices of bread, 1 slice of ham. It's really not making him like an artist. Like, hey, 1 slice of, slap it together, boom, throw it over. So if he is making, if we know this number, so that change in concentration of bread is 20 sandwiches per unit of time. Okay? That's what that means. Okay, hey, that's going to increase. Now, what that means is because of the fact that these are all equalities, that means the ham is going, the concentration of the ham, because those are in a 1-to-1 ratio, okay? So the sandwiches and the ham are in a 1-to-1 ratio. So as one goes down, that has to change in a 1-to-1 ratio. So that means the change in concentration of the ham is going to be -20. So the ham is going to be, that change in concentration would be -20 slices of ham per unit of time. Okay? Whatever that is, per minute, whatever that is. Okay? Now, next up, if you look at what's going to happen to the bread, okay? So if you want, so this is going to equal -1/2 times the change in concentration of the bread per unit of time. So if you know these numbers and you want to solve for the change in the concentration of bread per unit of time, and you want to get that by itself, what are you going to do? Multiply by 2. So to get this, you would multiply by 2, so that would become 40. So here, this is one approach. And like I said, some kids like this, because you really don't have to think. Oh, you just take 1 over whatever the coefficient is, and that's changing per unit of time, whatever that concentration is. Now, here's your other option. Some people like to approach this from a stoichiometric perspective. And you sit there and go, okay, well, if the change in the concentration of the sandwiches per each, right, is 20 sandwiches per unit of time. And then if you go to the stoich, you go, okay, well, let's look at the stoich, right? Okay, cool. So there is one sandwich, and that requires 2 slices of ham, and you multiply that by 2, and you get 40 that way. Okay? So I don't care how you want to think through this. If you want to think, hey, I don't want to complicate things with like the 1 over whatever and things like that, don't. Just look at it from a stoic perspective. The only time you would have to actually do that which is on the sheet where you have 1 over A, 1 over B, whatever, is if you were saying, hey, just write an expression for the rate function. If you were just straight up asked, like, hey, what's the equation to describe how these different things change, that's when you would have to do that. Now, interesting thing has happened here. So the solution started off clear. It's now blue. Why? Yes. Now, so again, what's happened? So we got this big mass of copper that was copper. Now it's basically all coated in silver crystals, but the solution has turned blue. So if you go back to that graph that we started with, so the silver concentration has gone down, and the copper concentration has gone up. And we know that because the solution turned blue, which is what copper ions look like. So now, over the period of time, these graphs are going to level up, okay? Because they're just going to reach that point of equilibrium where they're going to stay constant. Got the idea? Okay. Now, we're also going to use, wait for it, Q versus K. So we're going to go back and circle back to this idea again. So, what's the only time you use uppercase K?
Equilibrium.
So you're in equilibrium, okay? Now, just like anything else, it's going to be products over reactants. So if you were to look at this reaction that we just talked about for making sandwiches, and you had 2 slices of bread plus 1 slice of ham, you would need B2H. If you were to write this expression, assuming that these all, you could measure the concentrations, like sandwiches per room or sandwiches per sandwich bag or something like that. So it's still going to be the same idea. It's still going to be products over reactants. So this would be the concentration of the sandwiches divided by the concentration of the bread times the concentration of the ham. But I'm missing something. Will Stanley, what did I do wrong?
Oh, you forgot to square the bread.
Yeah, I forgot to square the bread, okay? Because of the fact that there's a coefficient of 2 in front of that. So if this was an equilibrium, so let's say, go back to this visual of the wall. Isaac is throwing completed sandwiches over the top. I'm disassembling them, and I'm throwing them back. So initially, Isaac is going to take the lead because he's throwing all these sandwiches over there, and I'm scrambling, okay? But eventually, I'm going to find my groove, okay? I'll say, hey, bring it, all right? So eventually, we're going to reach an equilibrium point where I'm going to know how many sandwiches are on my side, and at that equilibrium point, I'm going to know how many slices of bread and how many slices of ham are on his side. So just to make the math easy, let's just say that there are 128 sandwiches at equilibrium, okay? So at equilibrium, I have 128 sandwiches on my side. The slices of bread are at 4, and the slices of ham are at 4. I'm just making up these numbers because it's going to make the math work out nicely. So if I want to find, and this is important, if I know that this is at equilibrium, and this is important, if I know it's at equilibrium, this is the system is at its most stable form. Again, with these reactions, I'm going to put an arrow going in the reverse as well, because that means once you see these double arrows, that means we just don't make sandwiches. The sandwiches can decompose back into the slices of ham and the cheese. So if you were to do this, and we'd have 128 on top, then we'd have 4 squared down below times 4, if my math is right, that works out to be 2. So K would equal 2. Okay? Cool. Now, sometimes, but it's the same idea. What do you know about Ka values and Kb values and Ksp values?
Very small.
They're really, 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 really small, which means the forward reaction is not favored. Okay? K equals 1 is the break point. Big K values indicate what? It is favored. Okay? So if you have a really big K value, the forward reaction is going to be favored. So if you know, and don't look at this, there's a couple of weird things about K. Even though I preach units that are units that are extremely important, this one, K has no units. It's one of the very few times I'm telling you, hey, don't worry about the units. Mainly because of the fact that if something's squared, cubed, all of this stuff, it just gets wonky if you try and put the units with it. So this big K, and we're going to introduce a small, lowercase k in just a second. Sandy, you have a question?
Yeah, we're like that. When we're writing down our compounds, if one of them's insoluble, do we still have to write it?
Nope. Leave it out.
Okay.
Not part of the story. Like for this, I wouldn't talk about the concentration of the copper or the silver because it's a solid. It has to be something that you can express in terms of like molarity. Okay. All right. So K is going to equal 2. So when Mother Nature has reached this point of equilibrium, K has a value of 2. Now, we're going to change the numbers up a little bit. Okay? So now, I'm going to look at the same value of K, which is 2. Now, we're going to take a snapshot. And I'm going to tell you that the concentration of the sandwiches is 100. And the concentration of the bread is 2. And there's only 1 slice of ham. So this is 100. That's going to get squared. So I'm going to take 100 and divide that by 4, and I'm going to get 25. Okay? So this is my Q value. Remember QSP and KSP? If QSP was a lot bigger than KSP, what would happen? You make it precipitate because the system was out of equilibrium. There were too many ions in there. So in this situation, this is my Q value. Okay, this is a snapshot. So I said, hey, we walked in, and this is what we saw. Burkamp had 100 sandwiches. Isaac only had 2 slices of bread and 1 slice of ham. Okay? So the Q value is going to be 25. Now, Mother Nature at this point is out of equilibrium. So my Q value is bigger than my K value. Mother Nature doesn't like this. Okay? So mathematically, what's going to happen is that I've got to shrink this number. So what can I do to the concentration? So this is too big. Okay, this is too big. So what's going to happen? What's going to happen to the concentration of the sandwiches? It's got to go down. So I'm going to throw a whole bunch of sandwiches back over the wall towards Isaac. Isaac's going to get slammed, man. He's going to get slammed. So what's going to happen to the concentration of the bread and the ham, though? It's going to go back up. So if I shift the dynamic, if I know at equilibrium, K has a value of 2, And if Q is too big, Mother Nature goes, this is bad. This is bad. I got to do something. So in this situation, if Q is bigger than K, what's going to be favored? The forward reaction or the reverse reaction? The reverse. So what's going to happen is like I'm going to start chucking a whole bunch of sandwiches back over the wall, and Isaac is going to get slammed until we can reach like a new equilibrium again. Now, if the opposite had happened, let's say that I only had one sandwich. Okay, that's it. I have one sandwich. But if Isaac is sitting over there and he has like 10 slices of cheese and he has like 20 slices of, or 10 slices of bread and 20 slices of cheese. Now, I don't care about the number. What do you know about the value of Q? It's going to be big or small?
Small.
It's going to be small because I'm going to take 1 divided by basically 2,000. Okay? So Q here is going to be a much, much smaller than K. Q is going to be much smaller than K. Mother Nature wants to equalize things out. So what's going to happen to the concentration of the ham and the cheese? It's going to go down, but the concentration of the sandwiches is going to go up, okay, until we can reach a new equilibrium. So Q tells you in which direction the reaction is going to go, okay? If Q is too big, hey, we're going to shift that equilibrium. If Q is too small. Now, if we did this, we plugged in numbers and we got exactly 2, what would you know about the system? It's just an equilibrium, okay? Now, here's what a common misconception I want you to get out of your minds right now. Just because a system is in equilibrium does not mean that the reaction is stopped. All that means is that reverse and forward reactions are happening at a rate to maintain equilibrium, maintain that value of K. But you only do that when you have reactions where you have double arrows going in both directions. Okay. All right. Now, on this sheet, okay, on the front here, you've got, and this is how you can relate different things. And let me explain what this is going to be. Okay. Now, and this is where I always have to think literally which class am I giving this lecture in. So, in a physics class, R is the ideal gas law constant. And in a physics class, R has a value of 8.314 joules per mole Kelvin. Because in physics, we operate off the MKS system, meters, kilograms, seconds. Okay? So in a physics class, that's the value of R. Okay? In a chemistry class, because they like to be different, that value is still a constant, but that's 0.0821 liter atmospheres per mole Kelvin. So liter atmospheres are related to joules. And here's how this works. So joules is like a measure of energy, or it's a measure of work, okay? So liter atmospheres basically take the place of joules. So what this tells you is how you can relate a system that has Kc is concentration. Kp is based upon pressure. So when you're looking at the delta N, that's comparing total moles of gaseous reactant and total moles of product. And we're going to use delta N a lot when we get into something called entropy, which is a measure of disorder, gases have a lot more disorder than liquids or solids do. So this delta N thing will be used a lot. So it's basically a simple, easy way to look at, hey, what happens to the system? So if you look at that first reaction we talked about, okay, hey, we're going to take hydrogen gas, and we're going to react that with oxygen gas, and we're going to make water as a gas, okay? So it's always products minus reactants. So I've got 2 moles of gaseous product. I have a total of 3 moles of gaseous reactant. It isn't just one, it's whatever is the gas. Now, if that had been like solid iron reacting with oxygen, don't worry about the solid. This only works with gases. So what this allows you to do, like for example, if you know what the KC is, like for example, what we just did with the sandwiches, okay, and the concentration of the sandwiches per unit of time. So this would be the temperature that it would be run at. This would be the delta N. Now, it's the same mathematical idea. So if delta N, like in this situation, if I were to calculate delta N, I would have 2 minus 3, which would be negative 1. So what this means is that you would have to be given what the value of Kc is. Like you would say Kc has a value of something, okay? It's a number. R isn't going to change. Temperature has to be in Kelvin. Quick refresher. How do you convert from Celsius to Kelvin? Add 273 to it. This is what allows the units to work out. So in this situation, my delta N would be negative 1. So I'm going to take that to basically 1 over that because delta N is going to be a negative value. Now, delta N might be 0, okay? So if delta N equals 0, when you take anything and raise it to the 0 power, what do you get? 1. So if delta N is equal to 0, all that means is that Kp and Kc are the same thing. Okay? So this just allows you to work between a K value based upon concentration and a K value based upon pressure. So the Kp is pressures based upon gases. Kc is concentrations based upon like an aqueous solution, something like that. And again, it's like something Sun mentioned earlier. When you're dealing with concentration, do not worry about the solids. They are not part of the story. You only worry about things that you can talk about in terms of concentration. Okay. Now, this backside of this, do not worry about this. It's not going to be relevant. Okay? It will become very, very relevant for you tomorrow. I just don't want you to think about this like, God, do we have to have this memorized? No, don't. Okay? Eventually, this will all make sense. This is the preemptive, hey, don't flip out kind of thing. Okay, stop that camera. Stand up, take a quick stretch. I got one more thing.